Hello students, my name is Pragati Misra. In my last video, I was discussing about the partial differential equation. So those who want to learn about the partial differential equation, they can watch my previous videos. Today I will continue the topic group theory, and in which I will discuss group homomorphism today. So stay connected if you want to know about the group homomorphism. So we will start from the definition of group homomorphism, and the definition is, let G O, this is the first group G with the binary operation O, and this is the second group with the binary operation O dash, this is G dash. Let G O and G dash O dash be two groups. A mapping F from G to G dash is said to be a group homomorphism if f of A operation B is equals to f of A operation dash f of B, and this is true for any AB belongs to G. In a straight way, we can say that it preserves the group operation. For example, if we understand it graphically, then suppose this is our first group. I am just assuming it so that you can understand the definition of the homomorphism. So suppose this is our first group, and this is given with the binary operation O, and this is our second group, and this is G dash O dash. Now suppose there are two elements A and B. If these two elements are in this group and the group holds closure property, then their product or if we apply the binary operation over these two elements that must belong to the given group, because this is a group, then there must exist an element here corresponding to this element that is known as f of A. And for this element there exists an element f of B, and for this element there must exist an element of the form f of, for this element, A operation B. Since these are two elements and this is again forming a group, so there in this group again closure property holds. So if we take these two elements and apply the binary operation of this group over them, then that must belongs to the given group, and that will be equal to this element. So this implies that the group homomorphism preserves the group operation. Now this will be equal to f of A operation dash f of B. So in this way we can understand it easily, that the group homomorphism preserves the group operation. Now we will take some examples to understand it clearly. So our first example is, let Z is equals to set of integers with the positive operation, and Z dash is equals to 2 power m such that m belongs to Z, and this group is defined over the binary operation multiplication, and this group contains all the elements of this form, that is 2 raised to power m, where m is coming from the set of integers. These are two groups. Then a mapping f from G to G dash given by, this mapping is defined with this function, that is f of m, where m is belonging to G. If we take any m from G, then this goes to the element 2 raised to power m. And if the function is this, then we have to prove that this function is forming a group homomorphism. Then how we can show this? We have to just apply this condition over here. If this condition is satisfied, then we can say that the given function is forming a group homomorphism. So the condition of group homomorphism is it that f of A operation B should be equal to f of A operation dash f of B. Now firstly we have to take two elements of the first group. So I am taking m and n, two integers, and this is true for any, or for if m comma n belongs to the first group Z. Then we have to apply the given condition of homomorphism, f of m plus n, because the binary operation for the first group is addition. So we have to apply this. That will be equal to 2 raised to power, according to the given function, 2 raised to power m plus n, and we can write it as 2 raised to power m into 2 raised to power n by using the property. So what it becomes, this is equals to f of m actually according to the given function. So this becomes f of m into f of n. Now what we get, that it is preserving the group operation, because we have taken the first operation, that is the addition of the first group, and then we got the second operation in the right side. So it preserves the group operation. So the given function is a group homomorphism. So F is a group homomorphism. Now there is a note point, that is a homomorphism of a group into itself. That is, suppose this mapping is taking place from the same group to the same group. That is, this G dash is replaced by the G. That is, we are taking the group homomorphism from the given group to the given group again. In that case, this homomorphism is called an endomorphism. So always remember, if the homomorphism is given from the same group to same group, then that is called an endomorphism. So now we will discuss about the group isomorphism. So in general, we can say that a bijective group homomorphism is called an isomorphism. Bijective means what? It should be 1, 1 and onto. So the same mapping with the same groups, that is, if GO and G dash O dash are two groups, then the mapping F such that G to G dash is called an isomorphism if F is 1, 1 and F is onto. That is, F should be bijective and it should satisfy the condition of the group homomorphism. If these three conditions are satisfied, then we can say that the given function F is an isomorphism. And then the two groups G and G dash are said to be isomorphic and the function will be isomorphic. Okay, so the groups G, O and G dash, O dash are isomorphic to each other, and this is denoted by G is isomorphic to G dash. So this is the symbol to denote a isomorphism between two groups. So our first example is, suppose R plus denotes the multiplicative group of all positive real numbers and R is the additive group of all real numbers. Then the mapping F such that R plus to R given by this function f of x is equals to log x for all x belonging to the first group R plus is an isomorphism. Then R plus is isomorphic to R. We have to show this. In order to show that these two groups R plus and R are isomorphic together, we have to show first that this is a bijective function, this f is bijective, and then we have to show that this f is a group homomorphism. If these three conditions are satisfied, then we can say that the given group are isomorphic to each other. So firstly we show that the function is 1, 1. So how to show that the function is 1, 1? We all know about the 1, 1 condition, that is, if two elements are distinct, then their images should be distinct. That is, if x is equals to y, then fx should be equal to f of y. Or if x is not equal to y, then f of x should not be equal to f of y. So we can also start from the reverse, that is, if their images are equal, then the pre-images must be equal. So we will take from here. Okay, so if f of x is equals to f of y, then by the given function we can write that log x is equals to log y. And if we take the anti-log on both sides, we can get x is equals to y. So what we get actually, that for the two same images of two elements, the elements are also same. That is, if their images are same, then the elements must be same. So the function is 1, 1. Now we show the condition of onto. In order to show that the given function is onto, we have to take one element from the codomain, and we have to show that every element of the codomain must exist a pre-image in the domain, and this is true for every element of codomain. We have to show this. So if we take any y from the codomain, that is the set of real number with respect to the additive group. So if we take any element from this group, then there must exist a pre-image for this group. So we can take it, there exists e raised to power y. Why I am taking e raised to power y? Because if we apply this function in the given function log x, then this becomes log e base e power y, and this gives only y here. So we can take this element for the pre-image of y, and this belongs to the R plus, such that if we apply it over the given function, so this becomes log e raised to power y. Now the value of this term becomes y only. So the mapping is onto clearly. So F is onto. Now we have to show the last property, that F is a group homomorphism. So if we see that our first group, that this was defined with respect to the multiplication, and the second group was defined with respect to the addition. So if we apply the condition of homomorphism over here, then this becomes F of xy. I am taking here the binary operation as the multiplication because the first group is defined with respect to the multiplication. Now this can be written as, by using the given function, it becomes log of xy, since it is defined in the example, and this is true for all xy belongs to R plus. Now if we use the property of log, then this becomes log x plus log y. Log x can be written as f of x, and this can be written as f of y. So the condition of homomorphism is also satisfied. So we can see that all the condition of isomorphism is satisfied in this example. So R plus is isomorphic to R, and in this way we can prove that the given two groups are isomorphic to each other. I hope you understand the concept of group homomorphism and isomorphism, and I hope you like my content. If you are liking my content, please subscribe my channel. Thank you.